Hi guys, this is Rakesh Sir and I welcome you to the Concept Capsule, the GATE 23 Concept Capsule, where we are taking up small but yet important concepts to be delivered to you within small time. So yes, these short videos, small videos are targeting some important topics of the GATE examination. So ripple counters from digital electronics is always an important topic, and let me in this very small video give you the different type of questions that you can expect so that you can practice little bit further on this. So let's get started quickly guys. This is a brief intro about me. This is Rakesh. I have secured All India rank 9th in GATE examination and completed my masters from Indian Institute of Science, Bangalore. My major area of expertise is control system, digital electronics, signal and system, electromagnetic theory, and I also deal with the maths and aptitude. Ripple counters guys, against two synchronous counters. So just have a quick recall what synchronous counters are. Synchronous counters are one in which all the flip-flops are connected by a common clock. They are synchronized with the same clock. But in the ripple counters, which is a category of asynchronous counter, all the flip-flops are not connected by a common clock. So how they are connected? Rippling, okay, the propagating action. In the ripple counter, every flip-flop output transition will be serving as a source for triggering other flip-flops. In simple words, the output of every flip-flop serves as a clock to the next flip-flop. So where is the external clock applied? The external clock is applied to the LSB flip-flop. Let's have a look into the diagram and understand more. Diagrams will give you more clarity, and to understand, let's take a simple example of a 3-bit ripple up counter. Right, a 3-bit, and because I'm designing a 3-bit counter, I will be using 3 flip-flops. These are the 3 flip-flops, and you will be able to just see that this one is the LSB flip-flop, right? Q0, Q1, Q2 are the 3 output of the 3 flip-flops, Q0 being the LSB bit, and you are able to see the clock is served. The clock is served to the LSB flip-flop. The clock is served to the LSB flip-flop, and the output of LSB flip-flop goes as the clock for the next flip-flop. The output of the Q1, the output of the next flip-flop is now serving as a clock for the next flip-flop, and even if you want to go for a 4-bit counter, the output Q2 will be serving as a clock for the next flip-flop. And to make it as a ripple counter, all the flip-flops are in toggle mode. All the flip-flops should be in the toggle mode. Sir, what is the toggle mode of a flip-flop? Let's say you can design even using the JK. I have taken the example of T flip-flop, right? What do you mean by toggle mode? So let us just quickly recall. Everybody must be aware about this, right? T flip-flop, whenever the input T is equal to 0, there is no change in the state, right? The Q plus is equal to the Q plus I represent it as the next state. Q is suppose the current state, right? Whenever the T input is 1, the Q plus is known as the complement of Q, complement or toggle, right? So to toggle the device, toggle is just like complement. To toggle the device, the T input should be 1, and here I have set all the T inputs as 1. The flip-flop, all T flip-flop inputs are 1. Even if you want to design it using a JK flip-flop, all the JK input should be 1, because in a JK flip-flop, J equal to K equal to 1 corresponds to the complement condition, toggle condition, right? So you can do the same designing using the JK flip-flop. Both the JK flip-flop should be 1, 1, and correspondingly it is applicable to all the flip-flops, right? It will give the entirely same results. Now let us understand the functionality of this, and once if we understand, later on we are going to make it as a trick, as we know. Okay, so in this session, the concept of ripple counter, the calculation of ripple counter, the trick, and some questions I'll demonstrate to you. So just have a little bit of patience here. So let me just make the transition of the states. The states, let me write down the number. So now how a number is written? Number is always written from MSB to the LSB. So Q2 is the MSB, Q0 is the LSB, and as always by default we assume that any device will start from the power on state. Any device will be starting from what? Will be starting from the power on state. Okay, so the device is starting from 0, 0, 0. That's the initial state, or I can call it as the reset state, or I can call it as the power on state. Okay, now if the initial state is 0, 0, 0, where is the clock applied? Now see, clock is applied to the LSB flip-flop, and all the flip-flops are negative edge triggered. See guys, this is the symbol of a negative edge triggered device. If the bubble is not there, then it is a positive edge triggered flip-flop. And what is the meaning of negative edge triggered flip-flop? It will be triggered, it will toggle if it receives a negative edge on the clock. What is the meaning of negative edge? What is the meaning of negative edge, right? So clock is a periodic waveform. Suppose I have applied a periodic square waveform here, and whenever there is a negative edges on the clock, the flip-flop will toggle. Because the t input is 1, it is going to toggle. So if you apply t equal to 1, doesn't mean that the flip-flop is going to toggle immediately. It has to wait for the clock negative edge, because it is a negative edge trigger device. Negative edge means a transition from 1 to 0. Now to the LSB flip-flop, you have applied an external periodic clock pulse. That means after every certain time, which will be known as the time period of the clock, after every certain time, the negative edge will come to the LSB flip-flop and it will get toggled, right? Negative edge comes, the flip-flop will see the input is 1, so it will toggle the current state to produce the next state. So this will keep on toggling after every particular time. But what about the other? The others are not connected by the clock. So what is going to happen with the others? That is what I'm going to explain you here. So Q0 is the LSB, and every time, suppose the first negative edge of the clock comes, and this will be toggle is complement, so 0 is complemented to 1. Now, since the 0 is complemented to 1, what type of transition it is? It is a positive edge type of transition. Why I am looking into the transition of Q0? Why I am looking into the transition of Q0? Because this Q0 is going to the clock of the next flip-flop. This Q0 is going to the clock of the next flip-flop, right? And what type of transition occurs here right now? The transition that occurred here is 0 to 1, positive edge. So will the second flip-flop will respond? No, it will wait for negative edge. So this will be inactive. This will be inactive and it will remain in its same state. It will remain in its same state. So this will remain in the same state. There is no change. If it was 0, it remains to be 0, right? Now, the transition on Q1 actually will determine what will happen with the Q2, because the Q1 is connected to the next flip-flop clock. So what is the type of transition on Q1 right now? It is 0 and it remained at 0. So there is no transition, neither positive edge nor negative edge. So this device is also inactive right now and it will not change the state. So you get the next state as 001. You get the next state as 001. Now again, after certain time, after a fixed interval of time, the clock will come to the LSB flip-flop and it will again toggle. It will again toggle. It will again toggle, right? Acha, it is also very much clear with this operation ki when should the clock come to the LSB flip-flop? What should be the minimum value of the time clock period? Okay, that is a separate topic, that is a separate concept, but let me just give you an idea, right? First the LSB. Okay, then you have to wait for the second bit whether it toggles or not. Then you have to wait for the third bit whether it toggles or not, right? So how many cycles are involved, right? Before the next clock edge, before this makes a transition, right? First, this will make complete transition, then this may or may not, but you have to at least check, and then this may or may not, right? What is the worst case wait for the clock period? What is the worst case wait for the clock period? The clock period should be greater than the propagation delays of the individual flip-flops. The propagation delay of the individual flip-flop. If they are equal, this should be 3 TPD. TPD I am assuming as the propagation delay of one flip-flop, right? Chalo, let's not go into that point much. First, let us complete this table. So what I am telling, again after a certain period of time, the clock will be coming to the Q0 and it will get toggle. And now you see what is this type of transition? 1 to 0. On the Q0 you see 1 to 0 transition, that is known as a negative edge. That is known as a negative edge, and because there is a negative edge here, sir, this is 1 to 0, so this flip-flop will also be active. It will read the input which is constant 1, so it will also toggle. So there will be a toggle on the Q1. There will be a toggle on the Q1 which is 0 to 1. But what is this type of transition on Q1? Guys, it is a positive edge, and on the positive edge, the next flip-flop will not respond. The next flip-flop will not respond. So that's what you have to keep doing. You have to notice the transition on every flip-flop. If it is a negative edge, the next flip-flop will toggle. Otherwise, the next flip-flop is on the same state, right? So this is a positive edge. So the next flip-flop is still inactive and it will remain in its previous state. Guys, again after a certain time, the clock will be coming to the LSB flip-flop. It toggles and it becomes 1. It toggles, it becomes 1. What is this type of transition now? Positive. I'm again repeating to you, right? Look at the transition of a flip-flop. If it is negative edge, the next flip-flop will toggle, otherwise not. That is the moral of the story now. So what is this edge? Positive edge. Okay, so next flip-flop, sir, no change. 1 remains and 1. What is this edge? So this is no edge. Okay, so next flip-flop, sir, unaffected, remains in the same state. It is 0. So you're able to see one by one up counting is going on. 0, 1, 2, 3. In decimal, it is 0, 1, 2, 3. Again, after a certain period of time, the clock will come to the LSB flip-flop and it will toggle it. Now there is 1 to 0. Now there is 1 to 0, which is negative edge, and because of the negative edge, as soon as negative edge comes, next flip-flop toggle karenge. So this 1 toggles to 0, but now, this 1 toggle to 0, this 1 toggle to 0 is also a negative edge. And on the negative edge of a flip-flop, its next flip-flop should toggle. So its next flip-flop, which was at 1, which was at 0, will now become 1. Correspondingly, you get 100, which is decimal number 4, right? Again, after a certain period of time, LSB flip-flop will toggle. It will be converted to 1. What is this type of edge? This is a positive edge, right? I am not looking for positive edge. So positive edge matlab next, same. What is this 0 to 0? There is no edge. So next is same. 1, 0, 1, 5, right? You keep on solving, guys. You keep on solving. I'll quickly tell you 1, 0, 1. Again, the LSB flip-flop toggles. And 1 to 0 is a negative edge. As soon as negative edge, the next flip-flop will toggle. 0 to 1 is a positive edge, so next remains same. Again, after some time, LSB flip-flop toggle. 0 to 1 positive edge, the next is same. 1 to 1 no transition, same. 111, you get the highest 3-digit count. 111, that is decimal number 7. Again, after certain time, LSB flip-flop toggles. 1 to 0 is a negative edge, so the next flip-flop also ready for toggle. This also toggles, and this also shows a 1 to 0 negative edge transition, and its corresponding next flip-flop will also toggle. And where do you reach? You reach 0, 0, 0. You reach 0, 0, 0, which is the beginning state, which is the starting it, and hence flip-flop will keep counting. Flip-flop will keep counting from 0, 0, 0 to 1, 1, 1, and hence it is a 3-bit ripple up counter. 3-bit ripple up counter. Guys, now whenever there is a question coming on ripple counter, do you have to solve it every time? This, in competitive exam, this will take time, determining the next state of the LSB and then looking what type of edge it is. The connections may be different, right? According to this connection, it went up to be a up counter. So do I have to solve it, sir, every time? No, there is a simple method to observe. And actually, the questions of ripple counter will be more focused on reset pin rather than just counting. If counting is involved, this is very simple. Sir, why it is the simple? Let me give you a brief trick and brief conclusion about it. How do you identify a up or down ripple counter, right? Remember, for a ripple counter, the clock should be to the LSB flip-flop and all flip-flops are in the toggle mode, right? All flip-flops are in toggle mode. That is important. All flip-flops must be in toggle mode, okay? And one more thing, clock is connected to the LSB flip-flop, and after that you just have to see this, right? What you are able to see in the previous case, that Q output of every flip-flop is connected to the clock input. Okay, what type of clock? This is negative edge triggered clock. So the connection is Q to negative edge triggered. There are two types of tricks I will tell you. There are two types of tricks that you have to remember. Connection is Q to negative edge. So whenever there is a connection from Q to negative edge, it becomes an up counter. Now simply remember, even if you change one thing, up will become down, right? Suppose Q to negative change to positive. One thing you change, up becomes down. It is going to behave as a down counter. You can try it as a homework. Just change the edges of the flip-flop as positive edge triggered. It will behave 100% down, right? Q to positive. Now you take Q bar, only one change. Q bar to, this is Q to negative. Now you take Q bar to negative. One change, it becomes down, up to down, right? Q to positive. Q to negative we have seen. Q bar to positive, both change means up ka down, down ka up. Wapis it becomes up, right? Q to Q bar, negative to positive. So up to down, down to up, it is again up. Right? This is one way of remembering. So for this terminology, for this method, what you have to do? You have to just remember one thing. Q to negative edge is up, rest you can decide. Q to negative edge is up, rest you can decide. Okay. Acha sir, one more trick. Sir, tell me two tricks. Whatever is more comfortable you can remember. Okay. Right. Now let us call Q and Q bar. I'll give some terminology. I will give some terminology. Let us say Q is plus and Q bar is minus. Right? Let us say Q is plus, Q bar is minus. I am making a terminology, right? Positive edge, suppose, is plus, negative edge is known as minus. Now look into this. Look into this. Look into the first case, guys. First case, Q to negative. What is Q? Plus into minus. It is going into minus. What is plus into minus? Is minus. You have a up counter, right? Second, Q to positive. Q is plus. Positive is also plus. Plus into plus is plus, and it is a down counter. Case number 3, Q bar to negative. What is Q bar? What is negative? Minus. What is minus into minus? It is again plus, and it is a down counter. It is a down counter. Last case, Q bar, that is negative, into positive edge. Minus into plus is minus, and then it is again a up. Then it is again a plus. So what is the trick that you can develop from here? What is the trick that you can develop from here? Ki whenever it is negative, right, it is up. Whenever the result is positive, it behaves as down. Right? Whenever the final result after multiplying, what you are multiplying? The Q connection and the edge, right? Q for plus, Q bar for minus. Right. If the final result is minus, it is up. If the final result is plus, it is a down. That is also one more way of remembering. Or one more way of remembering is just remember one thing in mind. Q to negative edge, it's a up counter. Right. Just have a look at this very, very simple question. Figure shows a ripple counter using positive edge triggered flip-flops. If the present state of the counter is 011, what is the next state? If the present state of the counter is 011. Now see the type of connection. See the type of connection, guys. Very simply, within seconds you can solve, and these are like competitive level questions. What is this? Q bar to what type of flip-flop? Edge? Positive edge. All the flip-flops are positive edge. Q bar is known as minus, multiplied by plus. Minus into plus is minus. Minus into plus is minus, and negative pay you should have the up counter. Negative pay you should have the up counter, right? So if the current state is 011, next state should be plus 1. 3 plus 1 is 4. 3 plus 1 is 4. 100. Okay, you can solve these questions in 20-30 seconds maximum. That too, most of the time is for reading the question. Answer you can solve it in 10 seconds. The final answer is negative, and for negative I told you it has to be a up counter. It has to be a up counter. So up means it will go to the next state, increasing order. So 3 plus 1 is 4. Now guys, have a look into this. The circuit shown consists of JK flip-flops, each with an active low asynchronous reset pin. I will explain you this one also. This counter corresponding to the circuit is what type of counter? Modulo 6, modulo 5. Modulus is mod. Modulo means we all should know that. These are basic count terms. Modulo, also known as mod, is equal to number of states of the counter. Is equal to what is known as the number of states of the counter, right? So what is the number of states? Now it is looking like what? It is looking like what? Have a look at the connection, guys. Yeah, dekhenge. Have a look at this connection. The connection is all the flip-flops are in toggle mode. All JK1, all JK1, all JK1. Toggle mode hai. The clock is coming to the LSB flip-flop Q0. The clock is coming to the LSB flip-flop. So it is a ripple counter. Connection is Q to negative edge. And that is what we have learned actually. Q to negative edge is up. Or you can try once again. The Q means plus, negative means minus, plus into minus is minus, and minus is known as up counter. Minus is known as the up counter, right? So it is definitely a up counter. Okay, so the up counter will count from 0, 1, 2, 3, 4, 5, 6, 7 back to 0. Sir, is it modulo 8? But there is no option modulo 8. There is the reset pin. So if you understand this type of question, after that you can practice many types of questions. So what is the functionality of reset pin here? Try to understand. It is a modulo 5 counter. It is a modulo 8 counter in general. If I forget the reset, chalo. So it is a up counter, we know. It is a up counter. Q2, Q1, Q0. Right, 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. It will keep counting. Now look into the reset pin, right? Now look into the reset pin. Okay, what is driving the reset pin? The reset pin is being driven by the output of NAND gate. What is the type of reset they have given? Active low asynchronous reset. What is the meaning of this? The reset will work when you send a low signal to it. It is active when it is low. right? It is active when it is low, right? And block diagram you have to understand, whenever there is a R bar, it means active low, right? Either there is a R bar or there is a bubble, or maybe both. Either there is a bar, either there is a bubble, or there is a both. It means active low pin. It means active low pin. So it will be active. It will be active. Reset active. Okay, once it receives low, once X is equal to 0, because what is driving all the reset? The output of NAND gate, that is equal to X, right? What should be the value of X? X is the output of NAND gate whose inputs are Q2, and what is the next input? That is coming from Q0, right? What is the X? Q2, Q0 whole bar, and the output of the NAND gate is 0 if output of NAND gate is 0 if and only if both the inputs are high. If and only if both the inputs are high, right? So as soon as Q2 and Q0 are high, X will become 0. X goes to the reset pin. Then we will see what happens, right? So what you have to wait? Q2, Q0. You have to wait for Q2, Q0 to be 1. Right now they are at 0, 0. Earlier they were at 0, 1. Both have to be 1. So keep counting till that time. 0, 1, 1. 1, 0. Now Q2 is the 1, but Q0 is 0. 1, 0, 1. Now look at this. Look at this. 1, 0, 1. What happens? 1, 0, 1. Okay, this Q2 is high, this Q0 is high, this X becomes 0. This X becomes 0, and what is the type of reset pin? It is an asynchronous reset pin. Even if nothing is mentioned, by default you have to take it as asynchronous. Asynchronous reset pin means it will immediately reset the flip-flop without waiting for the clock. Asynchronous means not synchronized with the clock. Asynchronous means it is not in sync with clock. With clock, it will not wait for the next clock edge. As soon as X equal to 0, immediately it will reset, right? Immediately it will reset. So now I can say that Q2, Q1, Q0 is equal to 0, 0, 0 immediately. Immediately without waiting for clock. Without waiting for clock. And once it goes 0, 0, 0, it is in the initial state. Again it will go to 1, 2, 3, 4, right? So will this state be counted? No. This is a valid state, valid state, valid state, valid state, valid state. But as soon as the counter reaches 101, it is becoming reset immediately. So that means even if this state is there, it is there for a very negligible amount of time, and that is not a countable state. That is not a valid state. So how many states are valid? How many states are valid? 5 states are valid. It is a modulo 5 up counter. It is a modulo 5 binary up counter, option number A. It is a modulo 5 binary up counter, that is the option number A. That is known as the option number A. Suppose if reset was a synchronous pin, then your answer will be, think about this. If reset was a synchronous pin, then it will be a modulo 6. Then it will be a modulo 6. Why? Just I'll tell you. If it is synchronous means at 101 X will be 0, right? But it will wait for the next clock to make the flip-flops reset, right? So this particular state 101 will be active for 1 clock cycle, and hence it is a countable state. So 5 plus 1. Remember, always in the asynchronous and synchronous, mod number difference will be 1, right? If nothing is mentioned, sir, asynchronous. If intentionally they mention synchronous, then you have to take. Here they mentioned asynchronous, but there can be the case nothing is mentioned, right? So guys, I hope you have liked this concept. I tried to concise it in small time, but I think almost nearly 20-25 minutes I have taken. Okay, so yeah, more problems now you can solve. I've given you the brief idea ki how ripple counter counting is done and what is the functionality of reset pin. Hope you liked the video, and if you're liking it, do subscribe our channel for getting more such concept capsules and other videos. Thank you. Bye bye. Stay safe and take care.